Section 4.2 deals with the second derivative in graphs. Now recall in section 4.1 we saw that the first derivative will tell us where a function is increasing and decreasing. The second derivative of that function is going to talk to us about the concavity of a function. Now before we get to that, let's determine what the second derivative is. So the second derivative is just the derivative of the first derivative. And again, it helps us determine concavity. So some notations for the second derivative are f double prime of x, the second derivative of y with respect to x, and y double prime. So again, the second derivative is just the derivative of the first derivative. So if we skip down to number 3 real quick, and we want to find the second derivative, well, the first derivative we know, f prime of x, is equal to 4x cubed minus 18x squared plus 2. Now, if we want to find the second derivative, well, the second derivative, again, is just the derivative of the first derivative. So we're going to take the derivative of the derivative we just found. So here, we get 12x squared minus 36x. So the second derivative, and we'll finish example 3 later, but the second derivative is just the derivative of the first derivative. So what does it represent in a function? So concavity. Now let me show you concavity here. Concavity is either concave downward, as is this, or concave upward. It is what the shape of a graph looks like. So we say that the graph of a function is concave upward on some interval AB if the second derivative is greater than 0 for every x in AB. So you're concave upward if your second derivative is greater than 0. So if your second derivative is greater than 0, then you're concave upward. This also said, and I skipped over it, that f prime of x would be increasing. Well, that makes sense because if the second derivative is greater than 0, then that means that the first derivative should be increasing on that interval. We also note that the graph of f is concave downward if the second derivative is less than 0 for every x in your AB. So you are concave downward if your second derivative is less than 0. So if your second derivative is less than 0, you're concave downward. Again, if the second derivative is less than 0, then that first derivative would be decreasing. So you're also concave downward if your first derivative is decreasing. Now notice, first derivative increasing, first derivative decreasing does not correspond. This does not mean f prime of x greater than 0. That's not what that means, and this does not mean f prime of x is less than 0. It just means that the first derivative is going up from left to right, or the first derivative is going down from left to right. So you look at these 4 different things that I've broken up in concavity. So anytime you are concave downward, it means that your second derivative is less than 0. And anytime you're concave upward, it means that your second derivative is greater than 0. But I've broken it up a little bit more than that. So if you end up with a first derivative that is greater than 0, which means you are increasing, and your second derivative less than 0, you're going to look like the left side of a letter N. And over here, if your first derivative is negative or less than 0 and your second derivative is less than 0, you're going to look like the right side of this letter N. Here, if your second derivative is greater than 0 and your first derivative is less than 0, you're going to look like the left side of the U because you are decreasing and concave up. And here on the last one, if your first derivative is greater than 0 and your second derivative is greater than 0, then you look like the right side of the letter U because you are increasing in concave up. So if you are increasing in concave down, which is what this says, second derivative less than 0, first derivative greater than 0, you're going to look like the left side of the letter N. If you are decreasing concave down, so second derivative less than 0, first derivative less than 0, you look like the right side of the N. Decreasing concave up, first derivative less than 0, second derivative greater than 0, the left side of the U. And increasing concave up, second derivative greater than 0, first derivative greater than 0, right side of the U. So let's use all that information to find the following using this graph. It says the accompanying figure shows a portion of a graph of a function. We want to identify the intervals where the graph of this function is concave upward. So where does it look like the letter U? Well, it looks like the letter U from negative infinity to A, and then also from A all the way to the letter C. So we can say, okay, well that happens from negative infinity to C because this was a letter U and this is also a letter U. But notice here at C we start looking like the letter N. So that means we're concave downward in that section. So from C to, we stop looking like the letter N at the letter D. And then we start looking like a U again from D to E. And then from E all the way to G, we look like the letter N again. And then finally from G to infinity, I look like a letter U. So I am concave upward from negative infinity all the way to the letter C, and then again from D to E, and then again from G to positive infinity. And I'm concave downward from C to D, and from E to G. Now part C is asking us to identify the intervals where the second derivative is greater than 0. Well, that's asking us to figure out where we concave up. Well, that's going to be again from negative infinity to C, and then also D to E, and then finally from G to infinity. And part D is asking us to identify the intervals where the second derivative is less than 0. Well, that's the same thing as concave downward, which means from C to D and E to G. And then finally, this is going to be the same. It's asking us, where is the first derivative increasing? Well, the first derivative is increasing at the places where the second derivative is greater than 0, so part C and part E are the same. So A, C, and E all mean the same thing, negative infinity to C, D to E, and then G to infinity. And then part F is saying, okay, where is the first derivative decreasing? Well, that would be where the second derivative is less than 0, which means the same thing as part D. So part B, D, and F are the same, and that's going to be from C to D and E to G. The first derivative is increasing means that the second derivative is greater than 0, and the second derivative being greater than 0 means your function is concave up. Now the first derivative is decreasing means the second derivative is less than 0, and if the second derivative is less than 0, then the function is concave down. One last thing, an inflection point is a point on the graph of a continuous function f where your concavity changes. So anytime your concavity changes, you're going to have an inflection point. So for us, we would have an inflection point at the point x equals c because we go from being concave up to being concave down. Also at the point x equal d because we go from being concave down to up. And also at the point x equal e because we go from being concave up to down. And finally, at the point x equal g, because again, we go from being concave down to concave up. So anytime your concavity changes, you are going to have an inflection point. So let's figure out how would we find out all of this information if we're given a function instead of a graph. So to determine the intervals where you are concave up or down, the first thing you want to do is find the second derivative and find the partition numbers for the second derivative. Well, the partition numbers for the second derivative are going to be the same thing as the partition numbers for the first derivative. It's going to be where is the second derivative equal to 0 and where is the second derivative undefined. So we're going to figure out where is the second derivative equal to 0 and where is the second derivative undefined. Those are my partition numbers. Then we have to place those partition numbers on a number line. So this should be sounding very familiar. Part 3, select a test value from each of the sections and figure out the sign, positive or negative, of that second derivative in each one of those intervals. If the second derivative is greater than 0, you're concave up in that interval, and if the second derivative is less than 0, you're concave down. Now we don't have this listed here, but to find inflection points, if your concavity changes over x equals c, then you have an inflection point at c comma function's value at c. So points of inflection happen whenever your concavity changes. So if your concavity changes across one of your partition numbers, then that's going to be an inflection point as long as that number is actually part of the domain of the actual function. So if your concavity changes, but the number was not part of the domain, it's not a continuous function, so there's a vertical asymptote there, then you're not considered an inflection point. So let's look at example number 2. Example number 2 says find the intervals on which the graph of f is concave up and down and the x and y coordinates of all the inflection points. So let's start with finding that second derivative, which is our first step here. Well, we know that anytime we see a radical, the first thing we want to do is rewrite this without the radical. So f of x is really equal to x to the 1/3 power. So in order to find the second derivative, which is our step 1, the first thing that we need to do is find the first derivative. So the first derivative, f prime of x, would equal 1/3 x to the negative 2/3. Now that second derivative is going to equal, well, negative 2/3 times 1/3 is negative 2/9, x to the 1 less, so negative 5/3. So this is really the same as negative 2 over 9x to the 5/3. And then I have to find the partition numbers. So I need to figure out where is the second derivative equal to 0 and where is the second derivative undefined. Well, to set it equal to 0, I say negative 2 over 9x to the 5/3 equal to 0. I can always put my 0 over 1 and cross multiply to solve for x. Well, negative 2 times 1 is negative 2. And 0 times 9x to the 5/3 is 0. Well, negative 2 doesn't equal 0, which means there's no values of x where the second derivative is equal to 0. Is there any place where that second derivative is undefined? Yes. How do I know that? Because this is a rational function. So I set that denominator, which is 9x to the 5/3 equal to 0, and I solve it for x. And I'm just going to move this up a little bit. So first divide both sides by 9. And x to the 5/3 is equal to 0 because 0 divided by 9 is 0. And then you have to raise both sides to the reciprocal power. So I raise both sides to the 3/5. And I end up with x is equal to, well, 0 to the 3/5 is 0. So is 0 part of the domain of the original function? Cubed root of x, can you take the cubed root of 0? Yeah, you sure can. So 0 is going to be considered an inflection point if our concavity changes over that number. So I found my partition numbers. Then I place them on that number line. This is step 2. The only number I'm placing on here is 0. And then step 3, choose a test value from each one of those intervals. So from negative infinity to 0, I'm going to choose negative 1. And from 0 to positive infinity, I'm going to choose positive 1. And I plug them back into the second derivative and figure out if you end up with something positive or negative. So let's plug them into that second derivative. Negative 2 divided by, in parentheses, 9 times negative 1, raise that to the 5/3. So I have negative 2 divided by 9 times negative 1 raised to the 5/3. I hit enter and I end up with something that is positive. So f double prime of x here is going to be something positive. So if I'm positive, that means that in this interval, I am concave up. Let's see what happens at positive 1. Again, we're just going to stick it in the calculator to figure that out. So we're going to say negative 2 divided by, parentheses, 9 times 1 raised to the 5/3. And I end up with negative 0.222, which means f double prime of, sorry, this should have said f double prime of negative 1 here. So f double prime of positive 1 is equal to something that's negative, which means that in this interval everything's negative, so I am concave down. Find the intervals on the graph of f for which you're concave up and down. So we know that f of x is concave up from the interval of negative infinity all the way to 0, and it's concave down from that interval from 0 to positive infinity. Do I have an inflection point? Well, did I change concavity? I did, right? I went from concave up to down, and that happened at 0. So in order to find that inflection point, we know that the x value is 0. To find the y value, we have to plug 0 back into the original function. So if we're trying to find the cube root of 0, well, the cube root of 0 is 0. On our calculator, it would just be 0 to the 1/3. And so we have an inflection point at 0, 0. So we're concave up from negative infinity to 0, concave down from 0 to infinity, and we have an inflection point at 0, 0. Now, if we were to look at this graph, so x to the 1/3, notice that we are concave up, or we kind of look like a part of the letter U from negative infinity to 0, and then we start looking like the letter N from 0 to infinity. So we have a point of inflection, or our concavity changes at the point 0, 0, and we're concave up from negative infinity to 0, and concave down from 0 to positive infinity.